Hi everyone, my name is Savir Sharma, and we're part of the movie group. And our project is about modeling the spread of misinformation using reinforcement learning. And so the method of reinforcement learning that we're using is called Q-learning. And what's unique about Q-learning is it doesn't require any sort of framework, model, or even a database. And so what we do is we have our Q-learners, which is our reinforcement learning Q-learning agents, play games of NIM against other Q agents. And we track how our Q learner's ability to find the optimal strategy. So a little bit of background information about NIM. NIM is a two-player impartial game, meaning that all players have the same available moves. For example, chess is not impartial because one player can only use the white pieces and the other player can only use the black pieces. And so the setup of the game is you have a number of piles. Traditionally, there have been three, but you can have more or less. And you have a number of stones in each pile. And two players take turns alternating, removing a number of stones from a single pile. A player can either remove one or all of the stones in a pile, and the player to remove the last stone wins. What's unique about NIM is that it has been shown that there's an optimal strategy to NIM that can be calculated based on who goes first, the number of stones in each pile, and the number of piles. And you can mathematically calculate who is going to win that game just from this setup, assuming that they play optimally. And so next, I'd like to draw some analogies to real life. So the truth in the real world about any subject, something that is objectively true, is modeled as the optimal strategy to win. And so people in the real world, they're modeled as our Q learner. And so as a person goes about their day, they encounter perhaps information that is true. And so this is analogous to our Q learner playing a game of NIM against another Q agent. And this Q agent is an optimal agent. What that means is the opponent knows the optimal strategy, and they're going to use that optimal strategy. And so as our Q learner plays games of NIM against other agents that know the optimal strategy, they will also pick up on the strategy. And likewise, when someone in the real world comes across misinformation or information that's not true, that's analogous to our Q learner playing against a maloptimal agent. And the maloptimal agent does not use the optimal strategy. So this throws off our Q learner. And so as a person goes about their day, they do not come across solely true and solely false information. They come across a mixture of both. And we model this by having our Q learner play not only against optimal and maloptimal agents, but also random agents that use a mix of the two moves. And so next up, we have Aamod, who's going to talk a little bit about our methodologies.
We ran a series of experiments where we used multiple Q-learning agents playing against different opponents for a set number of episodes. The moves of our optimal agents are calculated mathematically and result in a NIM sum of 0. The moves of our maloptimal agents are moves that don't result in a NIM sum of 0. All of our Q-learning agents are parameterized as suggested by Eric Jarlberg's thesis, and we've used the Bellman equation to update the Q tables of these agents. We also experimented with adding a modifier that subtracts the predicted Q value of the future state, which we found improved the convergence rate of the Q learner. Theodore will now talk more about this.
So I created the 6 graphs on the right after adding the modifier that subtracts the predicted Q value of the future state from the temporal difference equation. And these 6 graphs show that the Q learner's ability to learn the optimal strategy or the truth against various mixtures of adversaries in playing the game of NIM. And the first 3 graphs show the Q learner's win rate and accuracy rate, which is the percentage of optimal moves by the Q learner against 50%, 0%, and 100% maloptimal agents. And the other percentage is the optimal agents. The final 3 graphs show the Q learner's win rate and accuracy rate against optimal, maloptimal, and random agents with the initial pile states of 3, 4, and 5. And in summary, these graphs show that the presence of truth tellers have beneficial effects for the Q learner to learn the optimal strategy or the truth. And Maryam will now talk about unlearning.
So one of the experiments we ran was called the unlearning experiment. So for this experiment, we divided the training period into 2 halves. In the first half, the Q agent played against mostly optimal agents, and this caused its convergence rate to go to 0 and its accuracy to also go to 1. And for the second half, it played against only maloptimal agents, and this caused its accuracy to decrease significantly, going all the way to 0.6. And this simulation models the individual who has been consuming truth for a period of time and suddenly is introduced to a brainwashing of misinformation, resulting in a decrease in accuracy as it forgets the truth. To mitigate this, we allow the Q agent to essentially judge its opponent after the first half. And to do this, it checks the opponent's actions against the optimal action for that state in its own Q table. And if these 2 actions are not the same, the learning rate is scaled by a multiplier of 0.1, giving less priority to agents that are different from it and more priority to agents that are more similar to it. And by giving less priority to differing opponents, the Q agent achieves a stable accuracy of 1, which means that is a successful mitigation. And this part of the simulation models a stubborn individual who is able to dodge a brainwashing of misinformation because they are able to resist the other ideas that are not similar to their own. Next, Aamod will talk about linear relationship of the Q table.
For this next experiment, we ran simulations with varying amounts of information given to the Q agent. We did this by changing the number of piles and stones in each game of NIM. After plotting the Q agent's Q table size and the episode the win rate converges, we found the graph on the left. And we noticed that this is a linear relationship.
Okay. The next thing that we did was we wanted to investigate the confirmation bias in society. We had an agent system whose initial strategies were not very similar to each other. And after only allowing them to play with other agents who had similar views as them, we found that there was a polarization of ideals, as seen on the graph here, where half the group converged to this optimal strategy and the other half of the group did not converge to any optimal strategy. So the 2 distinct clusters just proved that confirmation bias does in fact lead to a polarized society. And next, what we wanted to model was the current recommendation algorithms used by a lot of social media companies. Specifically, this one was modeled after the YouTube recommendation algorithm. So what these A graphs represent is just 2 different people with different political views. And the YouTube algorithm, what they would do is they would only recommend content that someone would watch. So therefore, if you were left-leaning, then YouTube would probably recommend you left-leaning content. And as you can see in this graph, so Q1 is an maloptimal leaning agent and Q2 is an optimal leaning agent. So as you can see in Q1, if it was just maloptimal and it only suggested maloptimal content, then you would get a strategy that was really bad. Whereas in Q2, which was an optimal agent, Q2 was an optimal agent, you would get a very high win rate and which converges. And what we found was YouTube recommendation also leads to polarization, and a specific strategy that can be used to reduce this polarization is you only need to recommend 1% of the other side's content. That would significantly reduce the polarization actually. But optimal percentages that we found are around 5 to 10%. And after recommending 10% of content from the other side, the effects are basically like diminishing returns. Next, Theodore would like to go over our conclusions.
So in conclusion, our approach created a new framework to model the spread of misinformation. And current research shows that reinforcement learning agents can accurately imitate human actions. And we have 4 key findings from our research. First is that polarization results. No, first is that the Q agent's rate of convergence is not affected by flagging posts. The second is that polarization results from confirmation bias. The third is that the technology firms' use of recommendation algorithms are further accelerating the polarization. And finally, that when people are more aware of how accurate the information provided to them is, misinformation is decreased.